Well, welcome back. Please take your seats. It's a great pleasure to announce this ICMP public lecture. So both here on site and online, you can listen to it either in English or in the French translation. So our lecturer today is Professor Michel Mayor. So Michel Mayor got his PhD at the Observatory of Geneva in 1971. So he's famous for discovering the first exoplanet orbiting around a sun-like star. And he got, for his research, a great number of distinctions and prizes. I would not be able to name all of them, but let me just name some. The Shaw Prize, the Kyoto Prize, the Wolf Prize, and in 2019, the Nobel Prize in Physics. Michel Mayor is a professor emeritus at the University of Geneva. Today, he will be speaking on other worlds in the cosmos, the search for planets similar to our Earth, and perhaps sheltering life. Michel, before giving you the floor, I would like to give you a small present. In fact, we prepared such presents for all our plenary lecturers, but that's the first occasion to give this small souvenir and also show it to the public. Michel, could you? So just a small memory.
Wow.
If you could.
Thank you so much. Thank you.
Well, thank you for...
So today, it's not mathematics. Yes, we have a little bit, but this is not the most important part of this lecture. Yes, I will try to give some hints of what is going on in this domain. Is strong enough? Ah, yes, yes. Yes, the present stage is evidently devoted to detect planets, to explore the mechanism of formation of planetary system, but evidently everybody is looking for the next step is to see if some of them have some form of life. So this will be typically what I would like to discuss. So the first question is when you are looking at a very teeny part of the Milky Way in the central part, you have this incredibly large number of stars. And in the Milky Way, you have something like 200 billion of stars, typically similar to the sun or not. And the evident questions, do we have planetary system orbiting these objects or not? And more, do we have some rocky planet with convenient conditions for the chemistry of life? So this was a typical question. Already some time ago, people was looking to answer this question. But what is not so well known that if the first part of the 20th century was already full of stories on extrasolar people and civilization and so on, in fact, for people working in astrophysics, the estimation of the number of planetary systems in the Milky Way was 0 or maybe 1 or 2. And it's only at the middle of the 20th century that we observe a drastic change of the estimation, and from almost 0 to going to 10 to the 12 or to 10 to the 10. And the present estimation are something like 100% of stars should have planetary system or something like this. Okay, we have a first reason why they changed their mind, but it was a very bad idea. I will not mention this. In fact, the real interesting comments was done by Otto Struve, it's an astronomer, and he observed that the rotational velocity of stars of low mass, typically with the mass of the sun or below, the rotational velocity is very small. This is absolutely not normal, because when you have a strong turbulence in the molecular cloud in the interstellar matter, when you have a collapse of this cloud, you are expecting a very large excess of angular momentum. And the observation reveals that the sun and other stars have a very low rotation rate. So Struve say, oh, probably the reason is because the excess of angular momentum went to form a disk of dust and gas. And so we are expecting that many, if not all, stars should have planetary systems. The reason why, during the first part of the 20th century, people believed that we do not have any other planetary system was because we do not have the good answer, the good reason to form accretion disk. Because the theory at the time was that we need to have a close encounter between two stars to have the possibility to pick part of the envelope and form a disk. And the probability to form such a system is extremely low, almost zero. So this was really it's a very small letter. It's 1 or 2 pages. So I like very much to repeat the name and mention the name of these two men. The first one, Otto Schmidt, is a Russian mathematician, and Viktor Safronov was one of his assistants. And they were the first to propose the correct scenario to form planet by accretion of planetesimal and to form planet by a long chain of physical process. Evidently, a lot of work has been done from that time. It was not an easy task, and still today we are missing some step. It's not so easy to clue some 1 meter rock or things like this. So not everything is understood. In fact, the existence of planetary disk of gas and, no, not planetary, this accretion disk of dust and gas was detected relatively in the beginning of the 70s, just by the excess of infrared light orbiting young stars. Here, no, it's okay. You have one, okay. I have some difficulty. You have the Planck emission curve of young stars, and you have a long, low wavelength excess of due to the dust. So this was indirectly detected, and immediately people realized that it is true. We have a lot of accretion disk orbiting young stars. Evidently, the final proof arrived in 1995 by the discovery of the directly imaging protoplanetary disk done by images of very young stars in front of the nebula of Orion Nebula. And these disks are dark because they are done by dust, and the dust is stopping the light coming from the nebula. At the same time, the difference of three days, we observed by the Doppler effect of some large sample of stars and Haute-Provence Observatory. We have developed this new kind of spectrograph, and the idea was really quite easy, that if you have the star here, you have a planet orbiting the star. In fact, evidently, the star is moving around the gravity center. And we have no chance, at the time at least, to observe the star, the planet itself, but we can see the small wobble of the velocity of the star. Evidently, the effect is very small because the mass of the star is much larger than the mass of the planet. And this was a very strange discovery because you see the mass, in fact, we have only an estimation of the mass at the time, was about half the mass of Jupiter, but the period was only 4.2 days. And the theory at the time said the mass of the Jovian planet, like Jupiter, Saturn, and so on, should have a period, the period should be at least of 10 years or more. So the discrepancy with the theory was something like a factor 1,000. So it's the reason why we have been a little bit careful before announcing this, and we have waited one season more to repeat the measurement. It was not the problem of the quality of the measurement; it was the problem of the interpretation. Because evidently, if you have a star with a small oscillation, you have a change of the velocity. If you have a star with a rotation with magnetic activity, you have a change of the velocity. So this was the reason why. But we have some argument to reject this possibility, and in 1995 we have announced this object. And it was very interesting to see first how this was interpreted. In fact, it was the discovery, the observed discovery of a very important phenomena, is the orbital migration. When you have the formation of the young planet in the disk, I have no chance with techniques. You have the young planet, and evidently the young planet will accrete the matter in a torus, and the mass of this young object will perturb the disk of dust and gas and induce some density wave at the position of the resonance. And evidently, you have a lot of different resonance. And if you integrate on the mass of these different resonance, the reaction on the orbit of the planet will be, in most of the case, a shrinking of the orbit, a spiraling of the planet towards the star. So this was, okay, the detail, the explanation is very simple, but after the detail could be much more complicated if you take into account the turbulence, the magnetic, and so on. But the basic phenomena is very simple. But what is strange, that this phenomena was already known and present in the literature from 15 years. You have a paper by Scott Tremaine and Peter Goldreich claiming exactly that we have to take into account. It was 15 years before, and nobody took into account this fact in observational strategy. Probably one of the reasons why people ignore this subject, this prediction, was the fact that the paper was devoted to the evolution of the orbit of small galaxies embedded in the disk of large galaxies. Typically, the stability of the Magellanic Clouds, the two small galaxies, and with a time life limited by this kind of phenomena. And it's only after the discovery of 51 PEG that people realize this is absolutely a major physical process in the formation of planetary system. And you see, this was not the only paper. Okay, you have the paper by Goldreich and Tremaine in 1980, but after you have a lot of other papers done by Papaloizou, Lin, and so on, discovering always the same phenomena. And it's only after 51 PEG discovery that people realize that we have to take into account this very, very important phenomena for the formation and evolution of planetary system. So now I jump by at least 15 years. This is a typical instrument we have right now in the Altiplano of Atacama Desert at 5,000 meters. And this is an interferometer with something like 60 dishes of 12 meters each, having the capability to observe the same object at the same time, and with the capability to be expanded from 200 meters to 14 kilometers to increase the resolution. And this is evidently, if it is at this altitude of 5,000 meters, it's because we should be above some pollution of water and so on in the atmosphere. So the resolution, at least when you have the largest distance, 14 kilometers, is extremely high. And you have evidently many different domains to be considered. This could be the formation of galaxies, formation of stars, formation of planets, and so on. All objects with cold gas. And at the time, they have observed some young stars, very young stars, and these famous accretion disks have been discovered, with always this kind of torus signature of the formation of planetary system. So today we have the capability to directly observe and characterize the chemistry, the density of this kind of accretion disk. Now I will go back to my favorite domain, and it's the Doppler effect. And evidently we are very happy that nature produces a lot of atomic lines in the spectra of cold stars, and it's only 1/10 of the domain we are using with our spectrograph. And you see we have thousands and thousands of atomic lines, very narrow. And this, all the difficulty will be to detect the shift, or the Doppler shift of this forest of line. But the difficulty is that, in fact, we have to detect Doppler shift about 10 to the 4 less than the smallest feature in this thing. So typically, the radial velocity change of the sun induced by the Earth is about 8 centimeters per second. So it's 0.3 times 10 minus 9 of the velocity of light and the wavelength. So it's extremely small, and this is really the difficulty of this problem, of this question. Just to have an idea of the technical progress made during the last 40 years, the first spectrograph we have developed based on what is called the cross-correlation technique. The idea is very, very simple. The spectra of stars is in a very large domain of temperature are not changing so much. So if you produce some kind of grid or a template of the spectra and you cross-correlate with the observed spectra, you can concentrate all the Doppler information of thousands of lines on one single quantity. And this is evidently needed because you don't have so much photons to do this kind of measurement. And the first spectrograph I produced with colleagues was Coravel with something like 300 meters per second. For dynamics of stars in the galaxy and things in globular cluster, it was perfect. But after the second one, LOD, a few years later, we arrive at something like a little bit more than 10 meters per second, is the spectrograph having allowed the discovery of the first planet. And then you see the last, no, not the last, ARPS spectrograph put in operation about 20 years ago, was arrived at 1 meter per second, and our last instrument, Espresso, is at the level of 0.1 meter per second, evidently on a much larger telescope you will see later. And also a lot of trick for the stability. So just to have view of the effect of this increase of precision, in fact, you have the first red dot to the left is 51 peg, a little bit less than Jupiter mass. The ordinate is the mass of the planet, is a logarithmic scale, and the years of discoveries of this object. And then after this first discovery, you see the explosion of the discoveries. At present time, we have something like 5,000 object discovery. But what is more spectacular is the increase of the precision due to the improvement of the instrument and strategy. And due to the different teams working in the world on this, we have been able to show that the most of the planets existing in the galaxy are low mass objects. Evidently, this is limited by the present precision, but you see that already we have a huge excess of planetary mass between few times the mass of the Earth. And it's very interesting because in the solar system, we do not have any planet between 1 and 10. And in our survey, these are the most frequent objects we are discovering. And below, evidently, this is still an open domain. So now the difficulties. We would like to detect rocky planet. Rocky planet is typically, if they are in the habitable zone, it's like the Earth, for example, the induced wobble is about 0.1 meter per second. So when I say we want to have the Doppler velocity of the planet, what is the meaning of this sentence? It's the mean velocity of the atom looking in your direction. But when you are looking in details the sun, you see that it's not so well defined because every cell in this picture, it's due to the convective cell going up and down with a velocity of typically 1,000 meters per second. And you have a magnetic field with a lot of magnetic activity, spots, and so on. You have acoustic mode and so on. So it's very noisy. It's absolutely not easy to have a precise velocity. So this is an enlarged view of this different cell. And you have a blue shift. It's a convective because the cell, when they are hot, they are moving in your direction. So it's a blue shift. So, and you see not all the lines are affected by at the same quantity by this effect. You see that if you measure the velocity of the different atomic line in the sun, you see they depend on the strength of the line. The largest one have almost the correct velocity, but all the thinnest one, the smallest one, have a strong blue shift because they are formed in different way in the atmosphere. So, okay, this is the difficulty. So some of my colleagues start a couple of years ago to use the same instrument we are using at night to observe stars, but observing with a small telescope, observing the sun, but with the capability to have really a global velocity of the sun and not a small point of the sun. And evidently, we have no pressure at all during the day. So we can do measurement every day, during several years, just to measure what is the velocity, the global velocity of the sun, apparent velocity. And we can see that you have the effect of the solar cycle, the magnetic activity. You have the change of the rotational velocity due to the existence of spot with something 30 days. The first one was a few years after 30 days. After you have active region, granulation, and acoustic mode. And so the velocity, observed velocity of stars is a mix of all these phenomena. So this is the result a few years ago. So you can see that the apparent velocity of the sun, global velocity, is changing by something like RMS, or larger than 1 meter per second. So it's 16 times larger than what we are looking for. So, and this is really a large source of concern, and applying different kind of filters, magnetic filters of this thing, we achieved to reduce the noise to something like 0.5 meter per second. Typically, the Earth of Moon induced a wobble is about 0.1 meter per second. So, okay, if you have a lot of measurement, okay, no, we are not too far. And a lot of people are working on this problem to see if we can improve a little bit the algorithm to decrease the noise. Evidently, you have the most serious problem is the problem of the signal treatment, but you have also the need to have a lot of photons, because to detect shifts of something like 10 to the 10 minus 10, so it's a very small shift, you need a lot of photons to have the capability to have this precision. And this is the last spectrograph, cross-correlation spectrograph, developed in particular in Geneva, but with a consortium of several colleagues at several institutes. And this instrument is located under the top of the mountain of Mount Paranal in Chile, with the capability to collect the light from the 4-8 meter telescope, and trying to achieve 10 centimeters per second. And not only can do a lot of other things, but evidently the first goal is the detection of and characterization of Earth-type planet. So now I would like just to show a different technique. Evidently, when we have discovered this kind of short period, tight orbits, short period orbit, in fact, the probability to have a transit is not negligible. Typically, for 51 pegs, the probability is about 5%. So if you have a collection of similar planets, we must have some transit. And this is very rich possibilities if we achieve to this, because in this sketch, you see, when the planet is in front of the star, you have a decrease of the luminosity of the star. And typically for a Jupiter-type planet, it's about 1%. For the Earth, it's 10 minus 4. Start to be difficult. When the planet go behind the star, in fact, you have a decrease of the infrared luminosity. And this gives access to the temperature of the planet, of the atmosphere of the planet. When you have phases like this, you have a modulation of the infrared, so give you some access to the thermal history, thermal physics of the atmosphere. And what is more interesting, in fact, you can see this small blue ring. This is the atmosphere of the planet, and this acts as a filter of the luminosity coming from the star. So the depth of the transit will depend if the atmosphere is opaque or not in this wavelength. So you can do some spectroscopy. You can analyze the chemistry of the planet, of the atmosphere, just looking the size of the transit for different wavelengths. So this is absolutely a fantastic technique. Evidently, you need to have a lot of photons again, because you have to compare always the spectra behind and in front of when the planet is in front. So in 2000, so 4 or 5 years after the discovery of 51 peg, the first transit was observed for a Jovian planet. It's typically, you see, this was about a little bit more than 1% of transit. The same measurement was repeated by our colleague, US colleague, but from above the atmosphere. And you see, this, okay, the scale is not the same, but the quality of the measurement you can have when you are above the atmosphere. So immediately you say, oh, we can dream to detect very, very low mass planet. But on an historical point of view, it was a very important, because the Doppler effect gives access to the mass. This gives access to the size of the planet, so it's not too difficult to determine the bulk density. And you see that the bulk density is 0.3 gram per cubic centimeter, and this is less than, for example, Saturn is 0.7. So this was a real proof that it was a gaseous giant planet. So evidently, people was quite interested by this technique, and this is, it was not maybe the final result, but this is a diagram showing in 2013, I believe, the radius versus the period in logarithmic scale in both directions of the discovery made by Kepler space mission. You see this, you have a lot of dots. If you have a black dot, it's only one planet orbiting. If it's a red dot, this corresponds to stars with 6 different planets orbiting the same star. So you see, it's multi-planetary systems are very, very common. And eventually, it's only a very small fraction of what exists, because I repeat, you need to have the good orbital plane to see the transit. So most of the transit are missing. And if the Kepler mission, I don't remember exactly the number, but was looking something like more than 100,000 stars during always during several years, like this. Every few minutes you take a picture. And then after a long series of measurements, and among them they have discovered something like 4,000 planets or planetary systems. And you see, so this is a very good observation that most of planetary systems are very thin. Okay, certainly it's not always the case, but certainly most of them are like this. You see also that the region where you can expect the Earth with a period of 300 days and a mass of 1 Earth mass is empty, because the probability is much less, and the lifetime of the mission was too short for that. Okay, we have some rocky planet in the habitable zone, but orbiting low mass stars where the habitable zone is closer. So, but you see also some objects have been detected with mass much less than the mass of the Earth. So this kind of technique opened a new field. I can call comparative planetology. We can start to do some physics with all these things. We have the, chemistry, temperature of the atmosphere, you have the period, you have and so on, and the size, and you can start to do some physics. And right now, for example, this diagram illustrates what we have for the relation between the radius versus mass of the object. Most of them coming from Kepler, but not all. We have some others. And this is the core of our program in La Palma Observatory. We have built a new spectrograph specifically devoted for that, to explore the domain of low-mass planet. And you can notice, for example, that rocky planet following a curve where you have the Earth and Venus are, up to about the mass of 5 times the mass of the Earth. So some rocky planet much more massive than the Earth should exist in the Milky Way. And then above this limit, you have a strong envelope, and the size is much larger. So the different curves correspond to different chemical composition of planets. This is part of geophysics. And for example, a larger view of this kind of exercise of research, you have the same time, on the left, you have the radius versus the mass, and you have the strip red for a rocky planet, and then after you have planet with large envelope going on a different slope. And on the right, you have a diagram of the density of the mean density of this object versus the radius. And you see that all the objects up to about 5 times the mass of the Earth have a mean density of something like 5, typically what we have for the Earth. So you see people are doing a lot of progress recently in the study of the bulk density of stars. And this is just a very short comment on what I mentioned, that just looking the contrast, the amplitude of the contrast of the transit, you can do some spectroscopy. And already today you see that a lot of different elements or molecules have been detected by this technique, simply because in some wavelengths the transit is larger than in others. And this is a huge domain for the future, because you need a huge, huge number of photons to do this. So you need to have big telescope to achieve this kind of precision. So next ambitious question. What is the meaning of this sentence? The Nobel Prize of Biology, Christian Ledoux, introduced this. If you have all the good conditions for the development of the chemistry of life, it could be a long series, evidently temperature, stability of the atmosphere, and so on. Do we have some expectation that life will emerge in the universe? So evidently in the lab, in the theory, we cannot predict answers to such a question. So at least in the first step, the best things to do is to observe and see if other convenient planets have life on their surface. And this is a very hot topic right now. And I will just give a few hints of how the way people are expecting. The first one was the first already mentioned, or something like 30 years ago, that, as you know, that the Earth's atmosphere has something like 20% of oxygen in the atmosphere, and we learned this at the elementary school, and it looks normal, but it's not normal, because the oxygen like to form some combination with rocks and to form oxide. And if you calculate the time life of the oxygen content, if you suppress all form of life, it is a few million years. So as the time life of the solar system is much, much larger than this, you need to replenish continuously the quantity of oxygen. And we have some alternative, but the most promising phenomena is biotic phenomena. So this 20% of life is directly related with existence of life. You see that you have these 3 curves was measured more than 30 years ago, something like this, observing by space probe the 3 planets, the 3 sisters, the Earth, Venus, and Mars, formed by the same procedure at the same time. And you see that at 9.7 micron, the Earth, the blue curve, has a very strong feature, is the ozone feature. So this will be one typical type of observation. Not easy to try to measure if some convenient planet have this kind of feature in the atmosphere. Why I say it's not so easy, because it's typically, we cannot do this from the ground, because it's typically the emission of any kind of body in the observatory, in the telescope, and so on. So this is one possibility. What is called, this is the detection of biomarker. And you can search for oxygen molecule, O2, you can search for methane, some nitrogen oxide, and so on. So you have different possibilities, but this is the most largest feature. Another possibility could be to see the equivalent of the seasonality, atmospheric seasonality of some biosignature. For example, this is the Earth, and you see for the upper curve, the carbon dioxide curve with a modulation of 1 year, because the biomass is not symmetric on the Earth, so the quantity of carbon dioxide in the atmosphere is changing with the season. So, and this is the same also for the methane. So if some similar feature could be detected in the future, in fact, this will be also a strong indication of the existence of a biomass. Still, a more indirect method could be to look the discontinuity of the chromatic curve of the reflectance and polarization of some biopigment. In fact, all biopigments, at least several, chlorophyll, carotenoid, and so on, have the same features, so they have the reflectance have a drastic change in the visible. And so if we can detect such kind of feature, will be also interesting. Personally, I believe it's very, very difficult, because if you have an ocean, the dark curve, the black curve to the right, kill completely this technique. And you are completely dominated after by the influence of the ocean. Okay, you see, it's not so evident. And maybe we have not to be over-optimistic that next year will be detected. So it's not so evident. Okay, people are building new instruments. And for example, you have a telescope of 39 meters. Okay, it's much larger than this room. This is a mind mirror. In construction in the desert of Atacama, at 3,800 meters. The beam, you can see this adaptive optics to correct the turbulence of the atmosphere. This was the status 2 years ago. The top of the mountain was flattened, and you have the basement of the telescope. You have some very nice study to do. You know, this is just close to the Atacama Fault. It's one of the most seismic region, dangerous in the world. But the sky is also very good. So the compromise is to nevertheless build the instrument at this place, but build some device, some trick to take care and compensate the risk of seismic threat. Because we are waiting for seismic Richter intensity of 9 in the future. So, for example, recently I discussed with a man involved in this kind of study. They put some sensor at few kilometers just to detect the arrival of the wave and to increase some protection, different kind of depression, oil pressure, and so on, for to avoid the damage. So it's absolutely fantastic type of technical development. Maybe it's not your most important source of pleasure, but it's very interesting. So just to compare, this is, you have the ELT, 39 meter, and at some place here, you can see the Hale telescope with this modest 5 meters of diameter. And evidently, for the ELT, it's not a single dish. It's something like 1,000 hexagon, with each one having different kind of size, form of shape, depending on the distance to the optical axis. So because you have to maintain the precision of a fraction of the wavelength. So if you are working at 1 micron, you should be at about 1/10 of micron of precision and so on. So on a surface larger than that. The James Webb Telescope, 6.5 meter telescope to be launched at the end of this year. Small, but in the space. And this is a short list of the different instruments. Transiting planet of bright stars, this is typically the topics of the different satellites, TESS, Cheops, Plato, James Webb. Doppler spectroscopy, different kind of instrument in different big telescope. Transmission spectroscopy to achieve planetary chemistry, temperature, biomarker, and so on, also linked to different kind of instrumentation.
Thanks a lot for this wonderful talk.